Okay, we're going to be looking at in section 2.7 here is some techniques for solving equations. Okay, and the equations that we're going to solve in particular are rational equations. So they're going to be equations that involve some of the rational functions that we've studied. Okay. There's one key piece of information that we need to be paying attention to when we're dealing with rational equations, and that's this idea of having extraneous solutions. Okay. Ultimately what happens is when we multiply or divide by an equation that contains variables, okay, the resulting equation may have solutions that are not solutions to the original equation, and we call these extraneous. Okay. And so very important when we're dealing with this type of equation that we must check the solution, okay, with the original equation when we get done. Now, if we're solving any equation, is there really any good reason not to check it no matter what kind of equation it is? And if there was an equation solving test, you should be able to tell me whether it's right or not. So we should always check regardless, but especially with this type of equation, okay, sometimes when we check the answers that we get, okay, they're not going to be correct answers after all. Okay. So a lot of times when we're dealing with these types of equations, which are rational ones, which we're going to see, okay, we might get solutions that don't actually work. Okay, so we're going to see how that works in a second. Okay. So before we start, though, looking at the solutions and testing them, we need to, first of all, talk about the techniques that are going to be used to solve this type of equation. So this would be a typical rational equation. It has a rational function in it. Okay, and the key technique is going to be what we call clearing fractions. Okay. So what we want to do here to clear the fractions in this is to decide what is the common denominator of all the fractions that are present. Well, this is not a fraction. This is a fraction. This is not a fraction. So there's only one fraction, so in this case the common denominator is pretty easy to decide about. Okay, it's just going to be the x minus 3. So the technique that we're going to use is to take the entire equation and then multiply it by that common denominator. Okay? So we're going to take that x minus 3 and we're going to multiply it by all the parts of the equation, in this case 3 parts. So with that said, we're going to get x minus 3 times x, which I'm going to write as x times x minus 3. Of course, I can expand that, but I'm going to leave that for the next part. Okay. When I multiply this x minus 3 times 1 over x minus 3, the x minus 3's will cancel out and leave us with just simply 1. And then on the right side, 1 times x minus 3 is going to be x minus 3. Okay. And again, that technique is called clearing fractions because what happened after we did that move? Okay. There are no more fractions. Okay. And that's the whole point, is to get rid of the fractions by making that first move. And then step 2, once we clear the fractions, is to solve the resulting equation. And if you look at the resulting equation, we have an x times x. It's going to be an x squared equation. This is going to be quadratic. So if we were to distribute here, we get x squared minus 3x plus 1 equals x minus 3. And then to solve a quadratic equation, we need to get everything on the same side. So we get x squared minus 4x plus 4 equals 0. Okay, and at that point, hopefully we can factor. If we can't factor, then we have no choice but to use the quadratic formula. Okay. And in this particular case, though, if we do factors of 4, and that give us a sum of negative 4, it would be x minus 2 and x minus 2 would be the two factors. If we were to unfoil that, foil it back to double check and make sure that's right, but that would be the factorization for that one. And then, of course, each of these could be set equal to 0. But since they're both the same, we really only do 1. So our solutions here would be 2, multiplicity 2, of course. But really, in the scheme of things, all we're after at this point is what x would make this sentence true. Okay, so our conjecture is that the answer is 2 here. However, we want to make sure that we check it to see if it's right. So if we put a 2 back into our original equation, okay, not into the transformed equation, keep in mind. We're going to put it back into the original equation and make sure it works. So we'd have 2 plus 1 over negative 1 would be negative 1. And 1 equals 1 would show us what about this x equals 2. That's right. It works. Okay, that 2 is, in fact, the solution. Okay. Now, I've mentioned this many times in this class, and I'll mention it again probably another 150 times. Okay. When we're especially in an equation solving problem, don't forget about what's the bigger picture here. Okay, when we want to solve an equation, all we care about really is when does this function equal this function. So if we're taking the ACT test in March, okay, and we look at this and say, oh crap, I can't remember back from December 3rd when we learned how to solve rational equations. Okay? If you have an ACT test that's a multiple choice test and you have a graphing calculator, do you need to remember how to do that? No. Okay? For me, do you need to know how to do that for my purposes? Yes. Okay, but not for the ACT test. Okay, but think about the bigger picture. If this is a calculator test, okay, you can check this also by using graphing. If I do x plus 1 divided by x minus 3, okay, that's going to be a function I can draw. And then, of course, on the right side, we have 1, which is just a horizontal line. Okay, all we really need to know is when do these two equal each other. So if we graph this, there's our rational function, and there's our 1, if you will. And if we use our intersection command, we can see it looks like, shockingly enough, it looks like 2 might be the answer, and oops, try that one more time. And yeah, you know what, that's going to have an issue because it's a double. It's got multiplicity too. So unless you put it in exactly the right spot. So I would suggest in this particular case, since it's a double, I mean if you look at it where they intersect, if you zoom in on that, probably the best case. Alright. The other way to tell too without having to use the intersection command, remember, is use the table. So if you look at your table and you look at 2, what do they both have as their y coordinates? They're both 2, 1. Okay. So you can tell that way also. Okay. Alright, but again, don't lose sight of the bigger picture here in terms of what are we really asking for when we're solving this equation. All we care about really is when does this curve equal this curve. Fair enough? Alright, let's take a look at another one. Okay. See how this one turns out. We have another rational equation. This one still has only one fraction in it, so therefore the common denominator is going to be easy to find in this case because it's just simply x. And then if we multiply x times each of the parts, x times x is x squared, 2 over x times x is 2, and then 3x here. And if we do x squared minus 3x plus 2 equals 0. And hopefully this factors, and in this particular case it does. And again, if it didn't factor, we'd have to use the quadratic formula. That would be our other choice. Okay. So it looks like we get 2 or 1 are the two answers that we get when we do the algebra. So checking them, if we did 2 plus 2 over 2 equals 3, we'd have 2 plus 1 equals 3, which we know is true. So that means 2 is good. Okay. 1, if we put a 1 plus 2 over 1, we get 1 plus 2 equals 3, which we also know is true. And so in this case, we'd get 2 answers. Okay. Both of them valid by the algebra. But once again, check by using the graph. If we were to type in our x plus 2 over x is 3. And we can see the two solutions there. Since it's not a double, the intersection command should work just fine this time. So we put it close to the intersection points. So 1, of course. And remember, when we're solving an equation that has x, are we concerned about what the y coordinate is here? Or all we want to know is what x makes this sentence true. So the y coordinate really doesn't matter. But if you do it again, just to double check, we can move it over to the other one. And hopefully, if we did this right, we should get 2. And in fact, we do. Okay. Questions so far? Alright, now this one is a little bit more complicated, okay, because we can see that there's 3 fractions instead of 1. Okay? And to get the common denominator, my suggestion to you would be to make sure that all of the denominators are factored first. Okay? Keep in mind, if it were just those two, okay, the common denominator would be those two multiplied together. Okay, think about why. If I had a 7 on the bottom and a 6 on the bottom, the common denominator would be 42. And how did I get that? 7 times 6. Okay, we can always get a common denominator by just multiplying the two together. So in this case, if it were just these two, it would be x minus 3 times x minus 1. Okay, now, if we're lucky in this particular case, what we have on this side, this quadratic, factors to those same two factors. Okay? And therefore, that is still the common denominator because each of these go into this, okay, evenly. So how's that going to look when we do the multiplication? When we multiply all three parts by x minus 3 times x minus 1. Okay, well, when we do this stuff times this one, the x minus 3 on the bottom is going to cancel out the x minus 3, and we're going to be left with x minus 1 times whatever we add on the top, which is 1. So we're going to have x minus 1 from that part, plus, now we'll do the same thing with this part, and again, this time the x minus 1s are going to cancel out, and we'll get 2x times x minus 3. And then on the right hand one, this stuff and this stuff will cancel out completely, and we'll just get simply 2. Okay, so again, that technique of multiplying by the common denominator clears all the fractions at the same time, which is the whole point. And then at this point, we got x minus 1 plus 2x squared minus 6x equals 2. Quadratic again, so 2x squared be minus 5x, and then minus 3. If we get everything on the same side, combine the like terms. Okay. And once again, hopefully this factors. If not, we'd have to use the quadratic formula. So let's see if it does. 2x and 2x. 3 and 1 would give me negative, positive would give me a negative 6 and a positive 1. So it does factor. Okay. And then if we solve each of these, 2x plus 1 equals 0, we'd get x equals negative 1/2. And x minus 3 equals 0, we get x equals 3. So again, at this point, our conjecture is that negative 1/2 is a solution here, and also 3 is a solution here. Now let's start with the 3 for the check part. Looking at what I have up top here, if I put a 3 in here, what's going to happen? It's not going to work, is it? Okay. So right away, I know that 3 is an extraneous solution. So even though we got that as a solution to the quadratic that we solved here, it's not, in fact, a solution to the original equation, is it? So therefore, we don't want it. We will not list that as one of our answers. Okay. Now, you can, of course, by hand put negative 1/2 into all that and make sure that's true. However, if I do 1 divided by x minus 3 plus 2x divided by x minus 1. And you'll notice that instead of that one thing that I did here is I made sure that this 2x here, if you don't put that 2x in parentheses, you're not going to get the right answer. Same thing with anything that's on the bottom or top of a fraction, put it in parentheses. We don't really need it for just a single number or a single letter. Okay, however, it wouldn't hurt to have it there. So if I were just you, if I had to type in any kind of division, okay, I would put the whole top and the whole bottom in its own parentheses and make sure that we got it right. Okay, Brandon?
You put in minus 2x.
Where?
In the calculator.
Thank you. Got it?
Yeah.
Alright, and then ultimately in this one it's going to be 2 divided by x squared minus 4x plus 3. Okay. And I don't have a very good window here, but let's go ahead and do a zoom 6 instead. Although we can't actually see that point there, but I'll still do a zoom 6 either way. So this is the graph of the left-hand side. Notice 2 asymptotes, negative 1 and 3. And there's the other one. Okay. And if you look here, I'm going to go ahead and zoom in on that spot where we see an intersection. There's the first function. And second function. And if we go ahead and use our intersection command, we can see that we do get, in fact, negative 0.5, the intersection between those two, okay, which verifies that that is a solution, whereas 3 is not. Alright. Questions so far?